Okay, so let's do this charge distribution. This is the arc of charge, and you can imagine if I just made that arc a little bit bigger, you can imagine that could be a semicircle. So what's nice is that I've never seen a problem where the point that they're asking for is not at the center. And so that's the one we're going to do. And so here's our arc of charge. And let's say that it has, the linear charge density lambda. And this is sort of part of a circle. So this we're going to call big R, that radius. This will also be that big R. Okay. The next thing we need to do, or so I'll just throw an R over here. The next thing we need to do is think about a little chunk dq. And what does the electric field at this point look like from dq? Well, it's going to look like that. So that's what our little dE looks like. And the value for that dE is, of course, k dq over r squared. So let's think a little bit more about what that could be. The r is the distance between the little dq and the point. So happily, that's actually a nice constant big R. Let's think a little bit about dq. All right. Let me do some other drawings. Sometimes it gets a little crowded. Oh my goodness, it's really hard drawing arcs. All right, so here's our dq. And I need to think maybe back on lambda. So what's lambda? Lambda is a charge per length, but in this case, it's a kind of length of arc, right? So if you're thinking, this is uniform density, so we can write d. Sometimes length of arc, that arc length is s, so we could write dq ds. How could we figure out what ds is? Well, it's this thing, and I kind of need to call that something. How about d theta? Does that work for you? And that's r. So hopefully you see that the arc length is r d theta. Okay, so in this case then, dq is lambda r d theta. All right, so we can plug that back up there. So k lambda r d theta. All right, we are in really good shape right now. Just for fun, let's simplify that. K lambda over r d theta. All right, that is our dE. So the next thing we need to do is kind of look at the symmetry of it, okay? So I'm going to go to another page. Okay, so our next step is to look at what other dQs contribute. Remember, the trick here is that electric field's a vector. So we have to actually, before we can just do that integral, we have to think a little bit more and see if we can see any symmetry. So this blue dQ is giving us this blue dE. I drew another little dQ, and hopefully you see why I did that, because of this lovely symmetry that you get. And then this guy gives that dE up there. So hopefully you see that symmetry, right? The only thing left is E sub x, right? And remember that this was theta, yeah? And so that's theta. So our dE is a dE sub x, which is dE cosine theta. Okay. I'll just remind you that last time we had this E sub x thing for the ring, we turned cosine theta into, we wanted to turn it back into like linear stuff, but now, do you remember that on the previous page, we had that our dE was k lambda over r d theta, right? Well, ooh, that's kind of nice. Here's a theta, but we're integrating over theta. So I think we're good. So it's now going to be reasonable for us to write the dEx as k lambda cosine theta over r d theta. All right, now we're cooking with gas. So that means our total EX is our integral of dEx. So we've got k lambda over r. Those are all lovely and constant. And we're doing cosine theta d theta. Well, we need to ask ourselves, what are our limits of integration? When you are given this problem, let me get a different color here, you will know, oh my goodness, that's, okay. Sorry, that was supposed to be the center. Now I just made that the center. This is a pretty horrible picture. But here's the thing. When you're given the arc, you're given this opening angle. Maybe call it phi. Okay? Of course, in a semicircle, right, if it went all the way, right, then it would be, the whole thing would be pi, right? So this would be like negative pi over 2 to pi over 2. So here it's negative phi. Oh, that's cute. I'm still in green. To phi. Okay, so take a second and make sure that makes sense. All right, so now it's pretty easy. The integral of cosine theta d theta, right? All right, so k lambda over r, and it's, the integral is sine theta, and this goes from negative phi to phi. So let's keep going. K lambda over r, so that's sine phi minus sine of negative phi. So we know sine's an odd function, so sine of negative phi is going to be negative sine phi, so we get 2 sine phi, so we get 2k lambda over r sine phi is our E sub x. And for a semicircle, then phi is pi over 2. And so you actually end up with 2k lambda over r for a semicircle. Okay, let's look at limiting cases. All right, so hopefully you knew I was about to ask, if something's far away, what does it look like? Hopefully you already have an idea, right? So if we have this tiny little arc of charge and I'm looking this far away, my gosh, it's probably gonna look like a point charge Q, right? Hopefully. But how do we calculate Q? Well, Q is gonna be lambda times, right, the length of the arc, sort of the fraction of the circle, right, if you wanna sort of think through it. So it's gonna be some fraction of the full circumference, right? What fraction is that? Well, it's the fraction of the angle over 2 pi, right? Right, and that full angle is 2 phi. Okay, so that angle is 2 phi, and so we're looking at that fraction of 2 pi, right? So Q is lambda. So what do you get? You get 2 phi r. And maybe you thought that what I just did was kind of overkill over here, and maybe you're just like, dude, it's just the angle times the radius. And that's cool. I was just trying to, if you can't remember that it's the angle times the radius, then you can reason through it with sort of what fraction of the circumference is it. Okay, so that number, 2 lambda phi r, it's just a number. Right? Phi is in radians. And for a semicircle, Q is going to be just lambda pi r. So just to give you sort of an idea there, right? Because phi was pi over 2. Okay? Okay, so a lot of times when we do these limiting cases, we look at our actual function, right, which was 2k lambda over r sine phi, and then we're like, oh, well, if we're far away, then, this variable goes to something, right? And in this case, it doesn't really work that way. There's nothing like that's obviously going somewhere. So sometimes they might just ask, what does the electric field look like? And so you look at that and you're like, oh, dude, it's a point charge, right? And so if you were asked to put it in context of this, right, you would put in your Q, which was 2 lambda phi r. So, I mean, it's just a number. It's not pretty, but it does definitely look like a point charge if you're far away. Alrighty.